So let's assume we've solved those equations for alpha and beta simultaneously. Then what do we find? Well, after a little bit of algebra and playing around, you find that you can then write f as IA over omega times sinh of sigma d into sinh of sigma y plus sinh of sigma d minus y minus ai divided by omega. So to do this, what have we done? We've used the fact that sinh of sigma, for example, is e to the sigma minus e to the minus sigma over 2. And there's a little bit of playing around to get it into this form. This is what we end up with. Okay, so that's effectively the problem solved now, because we found f, and that can then be substituted back into our original form for u, which is here. So now, having identified f, we can substitute it back into here, and in principle take the real part to find u. But we're not asked to do that in the question. We're asked to find the form of the shear stress for high frequency flow. So the shear stress on the wall is uy at y equals 0, so du by dy at y equals 0, and it's this quantity we're asked to determine when omega is large. So let's start by differentiating u with respect to y. So again, go back to the form for u. If I differentiate with respect to y, that's effectively differentiating f with respect to y. So we're going to need to look at f dash of 0. So let's take this form for f and differentiate it with respect to y. So f dash of y is ia over omega sinh sigma d into differentiate cosh sigma y, differentiate sinh sigma y, we get sigma cosh sigma y. Differentiate this one, we need to be a little bit careful because of the minus y in here. So if you do the chain rule, that's going to bring a minus sign out the front, and we'll get minus sigma times cosh of sigma d minus y. So that term you just need to be a little bit careful with. And that's constant, the minus ai over omega, so that differentiates away to 0. Then if we evaluate this at y equals 0, I've got f dash of 0 is ia over omega sinh sigma d into, well, there's a common factor of sigma here, let's take that out of the brackets. Then cosh of 0 is 1 minus, set y equals 0, I'm just left with cosh sigma d, like that. Right, now we need to think a little bit carefully about what's happening when omega is large. So let's just remember how we define sigma. So that's on the previous page. Somewhere on this page here, we define sigma squared is I omega. So sigma squared is I omega. Omega is real because it's the frequency. So if I work out what sigma is, this is root omega times I to the half. As an aside here, let's note that I is the same as e to the I pi over 2. So I to the half is e to the I pi over 4. Strictly speaking, plus or minus here, but we only need to take the plus sign. Okay, so sigma then is root omega times e to the I pi over 4. Now, what about something like cosh sigma d? So cosh of sigma d is by definition e to the sigma d plus e to the minus sigma d over 2. And sigma is root omega times e to the I pi over 4. So sigma is root omega times e to the I pi over 4, which is cos pi over 4 plus I sine pi over 4. Cos and sine pi over 4 are both 1 over root 2, so this is omega square root over root 2 into 1 plus I. Now, if omega is large, root omega is large, and the bit we care about in this exponential e to the sigma d is the real part of sigma. So here I've got an I contribution to sigma, which will give me an e to the I times root omega over 2 times d, but that's just oscillatory, it just involves causes and sines. The crucial bit here is the real part. So if omega is large, the real part of sigma is large, which means that this term is large, and that one is small, because that will be e to the minus root omega times a constant. So if omega is large, this term here is exponentially small. So if omega is very big, then in modulus, sigma also will be very big. And we can approximate cosh sigma d by just this term. The other one is exponentially small in comparison, so it's e to the sigma d over 2. And similarly, we can approximate sinh sigma d by the first term in sinh, which is exactly the same, e to the sigma d divided by 2.